In this demo, I will talk about the training process of a neural network using the following setting. Tanh with the activation learning rate with a 0.01 and the number of training steps with 500. The hidden space graph shows how the input data is transformed through the hidden layers of the network. The Tanh color decision boundary involves during training, gradually adjusting to effectively divide the cluster. By step 500, the boundary is well positioned, reflecting the network's ability to map the input data into a linear, separate hidden space. In the input space, we observe the neural network learning to separate the original data points. By the end of the 500 training steps, the boundary captured the nonlinear patterns in the data, demonstrating the power of the Tanh activation function to model complex relationships. The gradient visualization highlights the weight updates during training. Each line represents a connection between neurons, and its thickness indicates the magnitude of the gradient. Early in the training, the gradient are larger, resulting in significant updates to the weights. Over time, the gradients become smaller as the network converges and is stabilized. Now I apply the ReLU. With the ReLU, the training converges faster because the ReLU encourages sparsity and allows of efficient gradient flow. Now I apply the sigma activation function, where you can see using sigma, the training was noticeably slower. This is because the gradient in sigma tend to saturate for a large and a small inputs, leading to vanishing gradients. As a result, the decision boundary was less precise compared to Tanh or ReLU after 500 steps.